Okay, so let's see how we can avoid storing, computing the Fisher matrix computation, or working with the Fisher matrix. We can do this by not looking at the second order approximation and just looking at the first order approximation, and have just a Euclidean bound. And this is indeed the idea behind proximal policy optimization. It extends TRPO. It's actually a simpler version of TRPO, but in practice it works very well, and it's more efficient computationally. So our previous Lagrangian, right, that we discussed previously with the objective function, the loss function, the important sampling loss, minus our constraint, actually becomes something much simpler with the first order approximation, where we're trying to, again, maximize the expected minimum between, we'll choose the minimum, the pessimistic estimation between the important sampling ratio time the advantage function, so exactly this term. But we'll also consider a clipped version of this value, clipped version of the important sampling ratio, that is defined by the bound, the range that we define, right? The trust region that we define. Okay, these will be defined through the epsilon. We can either go an epsilon plus epsilon or minus epsilon in the important sampling ratio, but not beyond that. And again, as before, the rho, in this case, we've seen this before, we defined rho as the important sampling ratio, and A is the advantage function, or the approximated advantage function, and epsilon is the hyperparameter which defines our trust region, or which correlates to our trust region. And so indeed, this is the proximal policy optimization algorithm. The first term, the red one, we'll find the policy that maximizes return, assuming that the state distribution is similar to the old policy, right? This is the regular policy iteration step. But the second term modifies the surrogate objective by clipping our important sampling ratio, which removes the incentive for moving the IS ratio outside of the defined interval, 1 minus epsilon and 1 plus epsilon. Right, where 1 is an important sampling ratio of 1 means that we have similar policies, right? So plus epsilon, minus epsilon surrounding that. Oh, you can see how that correlates to the difference in the policies, right? A first order difference. We take the minimum here, so the final objective is lower bound, i.e. a pessimistic bound on the unclipped objective. This is mainly because we want to still have some monotonic improvement guarantees. However, we won't have them directly. We will have them under very specific assumptions which usually don't hold. But in practice, we'll see a general that PPO generally provides us with monotonic improvement, as opposed to other algorithms, right? So it's less noisy, some would say. In practice, not guaranteed for the general case. So we only ignore the change in probability ratio, right here, when it would make the objective improve. Okay, so again, we're always trying to keep a lower bound, a pessimistic bound on our loss, on our objective function. So in this is just a graphical representation of the clipped values for the important sampling ratio. Right, it depends, of course, if your advantage function is positive or negative. In any case, it will clip the values beyond a specific point, beyond the epsilon range, to be a pessimistic value, meaning that you'll never have an incentive to go beyond the trusted region, the region that we defined by the epsilon. Okay, so finally let's see some results for these trust region based methods. So these results are from continuous control benchmarks. Continuous control meaning that the action space comes from a continuous control, continuous values. The results present average normalized score over 21 runs of each one of the algorithms on 7 environments. For each algorithm, hyperparameters and hyperparameter setting. So for instance, there we are. We see here the results for PPO without any clipping or penalty. Then for clipping with specific different epsilon values. Right, no clipping or penalty is simply optimizing the advantage function. Clipping is the PPO algorithm, while KL penalty is the TRPO algorithm. Okay, this is what they mean. And you can see different hyperparameter values for the adaptive KL divergence, or the KL target value that is used to optimize the adaptive bound. We didn't see that. You can see the explanation in the paper. It just means, right, if you remember, we saw the beginning of this lecture, we saw that the trusted region bound should be adaptive, should increase or decrease based on how close your approximation is to the real value. So there are more specific ways to do it in each one of these algorithms, specifically for the adaptive KL bound. And you can see the exact results, the exact definition in the paper. It's not that important for our case. And also you can see results for fixed KL values. Well, these are just fixed KL values and they don't change over time. And indeed you can see that the best score over all of these runs is achieved by the PPO algorithm, which is definitely better than no clipping or penalty at all, than running a vanilla policy gradient. But it seems like clipping is indeed better, right? Let's see, for all of these values, for all of the epsilon values, no, not for all of them, right? So we have adaptive KL is actually pretty good here. But in general, we see that PPO, when tuned correctly, when choosing the correct hyperparameter, does indeed work pretty effectively, right? So it's both computationally more efficient and practically it provides better results. So PPO is considered a go-to algorithm these days, right? I would say this is one of the state-of-the-art algorithms that is commonly considered when just applying off-the-shelf RL to a given problem. Next, let's see some comparison or some results for the training curve. This is mainly to allows us to see if we indeed observe monotonic improvement over time. So these are comparison on several Mojuku environments. So again, robotic tests with continuous control. The x-axis here is the training step. So you can see that all training steps run till 1,000,000 steps in these results. And each one of the curves, the y-axis is the observed sum of reward, the J value. Okay, the expected, it's the average sum of discounted reward, which is a good approximation of J. So actually, the higher the curve is, the better. It means that it learned a better policy. And so we can see some results for we see the curves for several algorithms that we've discussed so far. A to C, the basic octocritic algorithm. You can see it in blue, and the interesting thing to see about basic A to C is actually here in the inverted pendulum domain. You see, also here, you see, specifically for this domain, you can see that the blue line here collapses quite significantly at some point. It learns, and then at some point it unlearns, and then it learns again, it recovers, but you cannot say that it provide results that seem like they're monotonically improvement, right? I mean, definitely we see quite a substantial dip here. A2C with trust region. So you can see that A2C plus trust region, a very simple approach to adding trust region to A2C, significantly helps with the monotonic improvement. It's still not always monotonic. Again, in the inverted pendulum you can still see some reduction in performance. But overall, once we consider trust region, you can see that it's very helpful. So this is just the simple actocritic approach, the advantage actocritic approach, where we enforce trust region by a conservative step size, right? And you can see that indeed this helps with more stable learning. CEM we didn't cover so far, so just ignore it for now. PPO algorithm. So you can see that PPO actually performs overall best in 1, 2, 3, 4, I would say 5. So in 5 out of the 7 domains here, it shows probably the fastest learning and mostly stable, right? You can still see that it's not it's not a monotonic improvement, but it does mostly show stable results. And if we look at the TRPO algorithm, actually when it does learn, you can see that this presents the most stable learning. However, in some cases, like here and here, it doesn't perform learning at all. Or it might be performed learning, but after much more steps. So it's not best with respect to sample efficiency, but it seems to be the most stable algorithm. Sometimes it's just stably, sometimes it's not learning in a very stable way, but it seems to be the most stable algorithm. And actually in one of these domains, the swimmer domain, it actually achieves the best results. Right? The fastest learning and also the best learning.
So,
any comments?
Why does it not perform as well as PPO if it's also doing trust region here? Is it because the approximated KL values are incorrect?
So that's an empirical question, right? Maybe it's due to approximation errors or noise in your approximation, which might be more substantial in this case. It's hard, so the why is hard to answer, right? Because you see that this is also non-consistent results. In one of the domains, it's actually better than PPO. So exactly why some domains are worse than others is hard to answer. Okay. And this is usually why we have I try to show you some empirical evaluations to show you that, well, these algorithms are very noisy, or the performance is very domain dependent.